Okay, Unit 6 now. Moving on, of our 9 units, so we're working all the way right through the course. This one is all about rational expressions, and it's mostly about the algebra behind rational expressions and rational functions. So can we actually rearrange these things and simplify them? Can we multiply, rearrange them? You've dealt with lots of rational numbers before, but they're usually just in the number version, and now we're going to be dealing with all the variables with them as well. And this is kind of an in-between, taking you from the algebra you already know with rational functions and getting you ready for in grade 12 when you're actually going to analyze the function itself and manipulate them. So, the first lesson actually I think is one of the easiest ones. I think it gets a little bit hard in this unit, but it starts out not too bad. So can we state the restrictions on rational expressions and can we simplify them? What is a rational expression? A rational expression is an algebraic fraction with a numerator and a denominator that are polynomials. What the heck does that mean? So it could be all sorts of things. It's a rational expression, something like 1 over x could be a rational expression. Or it could have variables on the top and the bottom. It could be longer polynomials on the top and the bottom, like y squared minus 1 all over y squared plus 2y plus 1. It could be all our regular polynomials are also rational expressions, if you like to think of like x squared minus 4. That's technically a rational expression as well, because you could always make it over a denominator of 1 as well. So there's a whole bunch of examples. These are actually our examples. The definition is an algebraic fraction with a numerator and denominator that are polynomials. So all of these things count. An example that doesn't count would be something like root of x all over x. Yeah, that's a fraction, but it's got a root involved. It's not a polynomial anymore. You also can't have like 1 over x, because the bottom, the denominator in this case, isn't a polynomial. So these ones are too complicated. They don't count. These ones are no good. As long as it's a polynomial on top and a polynomial on the bottom, that's generally what we're going to call our rational expressions, and leading into rational functions next year. So we've already dealt with a whole bunch of non-permissible values of root functions or root expressions. So now we have a new type of them, and these ones are a little bit easier, I think. A non-permissible value is any value for a variable that makes the expression undefined. For a rational expression, this is always when the denominator is 0. You're not allowed to divide by 0. So one new rule. So far, all of our restrictions are either the inside of the root cannot be negative, or a denominator cannot be 0. And this time we're dealing with this one. Make sure I got enough room here. Okay, determine the non-permissible values. What value makes this denominator 0? Well, x can't equal 3. Not 0, 3. Yeah, that's all it is. Just what value could you sub in to make it 0? This one's a little bit harder now. We have two different variables, s and r. So in this case, if s was equal to 0, that would be break it. So s cannot equal 0. And also, r cannot equal 0. If r was 0, then it would be 0 squared, which is still 0, and that would turn the whole bottom 0. So a pair of restrictions that time. This one, we factored, and this is just like finding the roots of a quadratic expression. So we're going to need our information from our quadratics units. This time x cannot equal 0. And then you have to solve for when 2x minus 3 is equal to 0. So you're going to add 3 divide by 2, so x cannot equal 3 halves. You could, of course, set that equal to 0 if you need to solve. 2x minus 3. When is that true? Oh, when that is the case. So you add the 3, divide by 2. In this one, so a little bit harder now. What value of p can you sub in to make it 0? You could do trial and error and just start subbing in values. Or you could be smart and factor it first. We're going to be doing a lot of factoring in this unit because our polynomials will often simplify after they're factored. So we actually don't like to see them in polynomial or expanded form. We like to see them in factored form. That's going to be our default in this unit. Every time we have a rational, we like to factor. So factoring the bottom, what adds to negative 12 and adds to negative 1 and multiplies to negative 12. So different signs, 4 and 3. So p minus 4, p plus 3. You should get really good at doing those simple ones in your head. I know all my grade 12s are very strong at that now, so it's going to take a lot of practice, but you should get very quick at that. You shouldn't have to do the whole product sum, writing down all the different factors every single time. You should be able to do some of them in your head. So in this case, p is not allowed to be 4, and p is not allowed to be negative 3. That's it for restrictions. Already a third of the way through this lesson. Okay, first of all, to simplify rational expressions, just going way back to, this is like grade 8, grade 9, I think it's before grade 9. Actually, we see things like this in grade 6, really. Equivalent expressions, you know, if you had the expression 1/2, you could change it to 2/4, you could change it to 6/12, you could change it to 48/96. All you have to do is multiply by a certain number every time. But the rule is you have to multiply the same number on the top and the bottom. As long as you do that, you're going to be fine. So the first one was times 2. Second one was times another 3. Third one was times another 8. So as long as you multiply by the same thing on the top and bottom, it's going to be fine. It's going to be equivalent. So now let's try the harder ones. Now with polynomials. If we had this expression, first we have to state the restriction. Now I can multiply by s on the top and the bottom to make an equivalent expression, which is a bit more complicated. So now I have 2 s's on the top, and I have an s times the s minus 2 on the bottom. In this case right here, we're going back to the original, and we're going to multiply by a binomial, s plus 2. So we're taking the top, and we're multiplying by s plus 2 to get to the new top. We're taking the bottom, we're multiplying it by s plus 2 to get to the new bottom. And we're stating the restrictions there. So we're going to be doing things like this to simplify. And we could go backwards as well, of course. If we had this, we could go back to the simple expression. And that's what we're going to be doing more often. So simplifying a rational expression, writing a rational number in lowest terms, and simplifying a rational involves similar steps. So writing a rational number in lowest terms, if you had this rational number, how do you write it in lowest terms? Well, you're going to divide by 3 to make it 3/4. And it's very similar to how we're going to simplify rational expressions as well. Now try simplifying by factoring and dividing both the numerator and denominator by factors. So the way we want to think about this step, instead of thinking of it like this, we want to think of it like this. 9 is actually 3 times 3. And 12 is actually 3 times 4. So it's like we common factored a certain number out to the front. If you can find the same common factor for both of them, those common factors will cancel. And that's how you get to your 3/4. Exact same reasoning, just a little bit different way of showing it. Okay, in this one, what do we have that's common? I'm going to do this one nice and slow, even though I think we can probably do this pretty quick. We have two m's that are common. Sorry, it's a little bit hard to see. I can bring this down a bit more. So there's two m's common in both of them, and there's one t that's common in both of them. So I could say there's an m squared t on the top, and what's left behind is 1m. And on the bottom, I have an m squared t, and what's left behind is 3 more t's. Okay? Now our common factors are the same, so they can disappear. So my expression is actually m over t cubed. Now when you're simplifying, the one thing you have to always remember, what we're saying is this expression is the exact same as this expression. If I subbed in a value for m and a value for t, whatever I got here is going to be the exact same thing as what I get here. And that's almost entirely true. And we could try a bunch of values. And why don't we try a couple values? Why don't we say m equals 1, t equals 2, or something like that. So in this original expression, I'm going to have 1 cubed, which is 1, times 2 is going to be 2. On the bottom, I'm going to have 1 squared is 1, 2 to the 4th is 16, so 1 times 16, so this is going to be 2/16 in my original expression. In my new expression, it's going to be 1 over t cubed, or 8. So my new expression is 1/8, and this is indeed true. All you have to do is simplify the first one, you end up at the second one. So this one is a nice, and it's simpler, but there's one exception. There's one reason why this is not the exact same expression as this one. And that thing is, if you said, what if m is equal to 0 and t is equal to 1, or something like this. This is just going to highlight the point. In my new expression, this is going to be 0 over 1. In my new expression, it's going to equal 0. In my old expression, well, the top 0 cubed is just 0 times t is going to be 0, so the top is 0. The bottom is going to be 0 squared, t to the 4th, so this actually all becomes 0 as well. And this number is not the same as 0. This number is undefined. So the new expression is almost always the exact same as the old expression. The only exception is the restrictions. You cannot sub in m equals 0. This is the thing that's not allowed. So we have to state the original restrictions and apply them to this one. The original restrictions is m can't equal 0 and t can't equal 0. And we still had the restriction t can't equal 0 in the new one, but we lost this one. This one disappeared. But even though we lost it, if we say it over here, then this is exactly equivalent to this expression. Otherwise it isn't. And that's a bit of a tricky thing to see right away. So that's why I say it nice and clearly. So even though you can simplify, you have to use the restrictions of the original expression. So let's try this one. Restrictions. S cannot be 2, and S cannot be -2. As long as we remember that, then we can simplify it, and it's still equivalent. So in this one, we actually have an s plus 2 in both of them, so they just disappear. So this one is 7s all over s minus 2. It's this with these restrictions. So you have to state both of those things, and then you have an equivalent simple expression. In this one, we actually have one s that's common, so one s is going to disappear from both of them. So on top we end up with 7s, on bottom we end up with s minus 2, by itself now. As long as we remember the restriction that s cannot be 2 and s cannot be 0. 2 restrictions, because you have to use the restrictions of the original. Good. Let's simplify some rational expressions. I think I'm going to give you a bit of time to do some of these ones. I'll just do A, and then you should probably pause and try a couple more on your own. So in A, we don't know what's going to cancel and factor out, basically, but we need to factor it first, and then we can find those things. So factor the top and factor the bottom. The top doesn't factor, but the bottom factors, and it factors 2, x minus 2, and 2x plus 5. So this is going to be a decomposition. And we've done a bunch of those recently, so hopefully you remember how to do that. So the top is 3x minus 6. The bottom is x minus 2, 2x plus 5. Adds to 1, multiplies to negative 20, break down the middle term, find your 2 roots. So it takes a little bit of time. Now, can we cancel? No, it doesn't look like it. It kind of looks like this one is very similar to this one, but not quite the same. So what we actually need to do is common factor the top as well. So we need to factor one more time. Let's pull out a 3. Then we end up with this whole thing, and now they cancel. So it's actually a fairly simple expression. It's just 3 all over 2x plus 5. It's only that expression as long as x is not equal to, from this one, negative 5 divided by 2, negative 5 halves. And remember the other one, which is x cannot be 2. State both restrictions. Good. Okay, you should try some more. Pause, try some more on your own. That might take hopefully 10 minutes or something. Okay, I'm going to start again. In B, you end up with the factored expression of y minus 2 times 2y minus 5. And on the bottom, y plus 5, y minus 2. Okay. Now you cancel out any terms that are the same. A y minus 2 divided by a y minus 2 is just 1, so it disappears. So our simple expression is 2y minus 5 all over y plus 5. As long as y is not allowed to... Now, from here to here, we didn't actually simplify the expression. So any restriction in this one is the exact same as the restriction in this one. We haven't manipulated it yet. So you have to go right back to the first step before you manipulated it. All we've done in this one is factor it, and factoring is completely the same. There's no change, there's no manipulation. So we can read them from this one, which is y is negative 5, y cannot be negative 5, and y cannot be 2. Okay, C was a fun little trick one, and you'll definitely see these. This is fairly common, so you should recognize what's going on in this one and become familiar with it. The bottom is a difference of squares. So it becomes t minus 1 and t plus 1. That is one of the tricky but very common difference of squares. You should always look for it, because the 1 counts as a perfect square. Now on the top, 1 minus t, that doesn't look like it cancels with any of these things. We could write it as, instead, negative t plus 1. And that's true, but it still doesn't look like any of these. And this is one of those reasons why we like to have a good form. Good form means all of our factored expressions, the leading term should be positive. If you always do that, it'll be in good form. And if you always do that, then you'll be able to find things that can cancel much easier. So changing this one to have a leading coefficient that's positive means common factoring -1 out. There's no other reason to common factor -1 other than put it in good form. So a negative t minus 1 is actually how we want to write that top expression. Put it in the right order and make the leading term positive. So now that cancels with that. And the answer is -1 all over t plus 1. Or the negative can be in the front, either way. As long as t is not -1 and t is not +1. Little comma. We put those after a comma usually. Yeah, that's it for that one. I would definitely keep an eye on that one. That's a very common. Sometimes you see this. The hard part is when you see this at the end of a long question. So you've already done a whole bunch of work. You've already done, say, some bigger canceling. And then you end up with something that looks like this. And it looks very small, so you say to yourself, oh, I'm probably done. I don't think anything else can happen. So keep a very close eye on those ones. They definitely come up all the time. This bottom one, so we're going to do the exact same thing. We're going to flip the top and common factor 2. So -2, it comes out and it becomes m minus 3. On the bottom, we can common factor 3. And then we have a difference of squareds, m squared minus 9, which is m plus 3, m minus 3. Good. If you do all that, then you find the things to cancel. So it's all about rigor. As long as you can turn these things into good looking form, then you can find the things to cancel really easy. If not, then you're going to be playing around with it for a long time. So -2 all over 3m plus 3. So long as m is not -3 and m is not +3. It's important to remember to common factor first as well. Otherwise this could have looked like, I don't even know what it would have looked like. But if you, so make sure you common factor first so you can find those roots. Good. If you felt very comfortable with this, then this whole lesson shouldn't be too bad. That was probably the hardest part. Rational expressions with pairs of non-permissible values. Okay. So, if we look at this expression right here, what expression represents the non-permissible values of x? It's unclear right now, right? So we would need to solve x in terms of y. There doesn't seem to be any x value that you could just sub in to make the whole bottom 0, but x relative to y, you can solve that. So we need to know when 8x minus 6y is equal to 0. So this says 8x cannot equal 6y, which means x cannot equal, not allowed, I should say that. Usually I add that at the end. 6 divided by 8, which is 3 over 4. So 3/4 of y. If x is 3/4 of the value of y, then this equation will break. So this is because there's two different variables now. This is less common, but it is something you should be able to do. Now we need to simplify the rational expression. So what can we do in this one? Well, on the top we have a difference of squares. Do we have a common factor? No. An even number, an odd number. No common factor. So the top is going to factor as 4x in the front and 3y in the back, and change the signs. just the square root of the front number, square root of the back number, and different signs. And the bottom, all we're going to do is pull out a common factor of 2, which leaves 4x minus 3y. Good. Now that we've done everything to make it look like good form, we can clearly see that that guy cancels with that guy. So on the top we have 4x plus 3y. On the bottom we have just the number 2, as long as x is not 3/4 of y. That's it. Show your expressions are equivalent by subbing in two values. X equals 2 plus 6 and y equals 1.2. So this is like a left side, right side check. We haven't actually done a lot of this year. I'm assuming you're familiar with this from grade 10. I think you even do it in grade 9 at times. If you're ever checking to see if two things are equivalent, you cannot use an equal sign in your checking. Because if you use an equal sign, if you check this is equal to this, the equals indicates you can move things to the left and right of it, but that's actually not allowed. If I set these two things equal to each other, and the first step maybe I move the 2 up to multiply the top, that already wouldn't be allowed. All I've done is proven it's equal if I assume it's equal. You're not allowed to assume it's equal if you're trying to prove it's equal. So you actually have to break it down, do each side individually. So on this side, we're going to end up with 16 times 2.6 squared minus 9 times 1.2 squared all over 8 times 2.6 minus 6 times 1.2. So we sub it in on the left and we sub it in on the right. So what is 4 times 2.6 plus 3 times 1.2 all over 2. So no moving things across this middle line. It's a hard barrier. Just simplify, solve the left and solve the right. And on the left side of this, we end up with the number 7 or thereabouts. Depends on how accurate you are. I assume this is rounded. Let me actually plug it in. I'll do it on the right side. On the right side, it's equal to exactly 7. On the left side, it's equal to exactly 7 as well. So not rounded, they're exactly equal. Which equals right side. So I've proven the left side is equal to the right side, and then we write QED, which means thus it is solved. Thus, what we set out to prove has been proven. The left side is the same as the right side. I'll try and do some more examples of this as we go along, but every time you check your work, you technically should do it that way. Sometimes if it's a really simple check, you could probably just say check, I'm checking these numbers, and you put a check mark after it. I just sub them in and I got the exact same thing. If it's simple, this one is a bit harder. This one takes steps, so you might have to show me. On a test, if it's a whole separate question that says show me, then you should show me with a left side, right side check. Don't just put a check mark at the end of a question. Okay, that's it for this one. 30 minutes long, not too bad. Try the assignment, try lots of questions. Again, it's about habit. Make sure you remember how to factor, make sure you know how to put it in good form, and then all you have to do is cancel things out and state your restrictions. Okay, good luck.